Welcome back, children. We have been discussing dipoles. We defined what a dipole is, and then we went on to find the value of the electric field produced by the dipole along its axis and also at a point on an equatorial plane. And these are the things that we have done with the dipole. We also did an example problem. I'm going to continue on the dipole a little more, maybe the last part of what is being discussed in the text about the dipoles. Okay, that is like keeping a dipole in an external electric field. You see, this is different from what we've done with the dipole so far. We found the electric field due to a dipole. Okay. There were two derivations that we went through, but those derivations were for the electric field produced by the dipole itself. But this is slightly different. This is, you have a dipole, you keep it in an external electric field produced by something else. Okay? It's like, you take a charge. If you take a charge, that charge will have an electric field due to itself. Right? The influence of the charge in the space around itself. Okay? That's the electric field. But this charge can be kept in the electric field of another charge. Right? Okay, we bring another charge, and that charge will have its own influence. Now, this charge is in the electric field of that charge. And that charge again is in the electric field produced by this charge. So this is what we call as external field. Like you have the charge, it produces its own field, well and good. But when you keep this charge in the electric field produced by another charge, then you call that as keeping the charge in an electric field, in an external electric field. That's what you say. So if you can do that for a charge, then you can do that for a dipole too. So you have a dipole. Now you're going to keep that charge in the electric field produced by you're going to keep the dipole in an electric field produced by another charge or a set of charges or a system of charges. Doesn't matter. So those charges, that system of charges has produced an electric field. Now you are taking the dipole and keeping it here. Well, will the dipole have its own electric field? Yes, it would, and that would affect that system of charges. But this dipole right now is going to be affected by the field produced by that system. Okay, so that is what we are going to do. This is an external electric field. But for our purposes, we are going to focus on a constant electric field produced by a system of charges. Okay. We don't know the nature of that system. We don't know how many charges constitute that system. We don't know how they are arranged in that system. We have no idea what's going on in that system. All that we know is that there is going to be an electric field produced by that system of charges. And this field is a constant electric field, meaning the E value, the magnitude of E, and then the direction of E will be the same at all the points in space. Okay? The best example we already discussed in the class is the gravitational field, right, near the surface of the Earth. So we talked about it. Like if I take the acceleration here, it's 9.8 meters per second squared, and if I take the acceleration here, it's also 9.8 meters per second squared, and then both of them are acting down, the same direction, same value, something like that. Okay? So like if you consider this thing, if considering an external electric field, which is a constant electric field, we are going to see what happens when you keep an electric dipole in that external electric field. Again I repeat, we don't know the nature of the source that creates it. We have no idea, we have not talked about it. But most certainly it's not a point charge. If it's a point charge, the external field was created by point charge, definitely you are not going to have a uniform electric field. Because as you move closer to the point, that point charge, then the field value will be stronger, and if you move away from the point charge, the field value will be weaker. Okay? And if you go to from one place to if I'm here, and if you go here, then clearly the direction of E will also be changing. Okay? So a point charge cannot create a uniform electric field. But let's assume that there is a system of charges, and we don't know what the nature of the system is. Let's assume that there is a system of charges that produces a uniform electric field, meaning the E value, the magnitude and direction of E is same at every point in space. That is a uniform electric field. The analogy that I've given you is that of gravity. So let's consider that such a field. So I take this, let's say like this, right? If you see the field lines of a uniform field, electric field, they will be parallel to each other, right? Because like at this point, I need to have some E and will have magnitude and direction. And if you take this point, there also I'll have the same magnitude and the same direction here. So here also the same magnitude and same direction. So if you look at this, the electric field lines of a uniform electric field will be parallel to each other. So that's my E. So uniform electric field. This is a uniform electric field. Okay. I'm going to keep my dipole in that field. Okay, so I'll use a different color for the dipole. So let's say this is E. This is E value. E is in this direction. So in this space, I'm going to keep a dipole, something like this. I have my positive plus Q here, and then I have my minus Q here. Minus Q here. So this is a dipole I'm going to use, okay? Then what do you think will happen? This is a dipole. Well, a dipole is basically a combination of two charges, a positive charge and a negative charge. And if I'm going to keep these two charges in an external electric field, they're going to experience a force. Each of them will experience a force. And let's see how the force would be. This is positive charge Q. The field is in this direction, which means that unit positive charge will repel in the direction, go in the direction. So this is a positive charge, and this will also experience a force in this direction. Okay? So the force experienced by positive charge is that in the direction. And what about the negative charge? The negative charge is going to be attracted in this direction, right? Because negative, if it were positive, it would have been repelled in the direction. But now it's negative, so this will try to move, or the force will act in a direction opposite to the direction of E. Right? Because E has a direction of unit positive discharge. But now you have a negative charge, so it's going to attract it in the opposite direction. So it's going to be in this direction. So this is the direction of the negative charge. Okay. So think about it. Think about it. Okay. I have this charge. This is a positive charge, it's a negative charge. This positive charge is going to experience the force in this direction. Something is going to push it in this direction. And what about this one? This is trying to go in this direction. Something is going to pull it in this direction, like this. So you see, this will go this way and this will go this way. You notice that this will start rotating. Okay? It will start rotating. So it will continue to rotate. Okay, it will experience a force, it will start rotating, and then when it comes here, at this very center when it is here, what's the force? There's a force in this direction, and there's a force in this direction. Okay, it's like this, force in this direction, there's a force in this direction, but both of them will act in opposite direction now. Okay, so the net force when it is in this position is 0. It's plus q. I mean, what's the force actually? Let's calculate the magnitude of force. What is F plus? F plus magnitude is going to be Q into E. Right? And what's the magnitude of F minus? F minus is also equal to Q into E, but only the direction changes. Okay, in both cases it's QE, QE. So what happens here is that this is going to be pushed in this direction, it's going to be pulled in this direction, it starts rotating, it does this, and then it gains some speed, then it starts rotating, so this gains speed, but when it is parallel to the field, then what's going to happen? This is going to be pulled in this direction, pushed in this direction, and this is going to be pulled in this direction. You see, it's like this. There is no rotation here actually, at this point. Okay? Because like just this. The two forces act along the same line, there will be no rotation. Like this, right? For example, if I take this foam, I push it this way, there is a force I apply in this direction, there is a force I apply in this direction, there is no rotation, I find. But slightly if you move away, you see, I push it this way, then rotation. Okay? So the same thing is what I'm talking about here. So it starts here, it goes this way, and it goes like this, it goes like this, it goes like this, and when it is parallel to the field, then the net force on it will be 0. The force is still FQ, it's also EQ. The force at this position is, in this direction it is QE, and in this direction it is QE, but they act in opposite directions, so net force will be 0. But would it stop? I mean, like, it won't stop, right? Because it has gained some speed up till here, so it won't stop, it will continue. Even though the net force is 0, then it will continue. Okay, then it will go like this, go like this, go like this, go like this. As it tries to go this way, what happens now? It will try to push it this way and it will try to push it this way. You see, once it has come here, from here, it goes this way, and then it comes here, and comes here. Net force is 0, then because it has moved this direction and it will continue to move, but as it continues to move, see what is going to happen here? It's going to be pushed in this direction, now it's going to be pulled in this direction. So now notice what is going to happen now. It will try to, it will try to rotate in this direction. It will still not rotate because it has gained some speed, it is there. From here, it's gained some speed, it is there, the speed is still there, but as it tries to go this way, the slowing down process happens. When it comes from here to this position, it speeds up. But when it tries to go down, then it's going to slow down because the force is going to be acting in this direction, force is going to be acting in this direction now. Now it will try to come back. So you see, then at some point it will stop. I mean, if there is no friction and nothing, then it will continue up till here, and then it will stop. As it stops here, because as it stops here, then it won't move. As it doesn't move, then the force is going to act in this direction, right? As it continues to act, then it will do this. Then it will continue here, then it goes here. And you see, then there is this oscillation that takes place, like this, like this. Okay, so think about it. It's very easy to visualize and see. Okay, it's here. Like I'm just keeping it here. Now it is at 0 speed, but then there is this pushing that is taking place. So it will start moving. It will gain speed. When it is here, even though the net force is 0, it has gained speed. So it will continue this direction. But as it comes below this point, then you see, the force, it will try to restore it, right? It moved from here to here, and now as it goes down, it will try to the forces will try to restore it back. It will slow it down. So when it is here, it will slow it down and it will come back. Same thing will happen. When it goes back like this, it will gain speed and here net zero, but it will continue with the speed. Then here it will restore, the speed will be made 0 and then it will continue to do this. So this oscillation will happen. So the electric dipole will keep oscillating about this point. Okay. But because it is oscillating, I should be able to find the torque, right? Because like it's rotating. There is a rotation, it's kind of rotation there. So I should be able to find the torque. Can I find the torque? Well, it is going to rotate about this point, right? It's going to rotate about this point. So the torque, I can, from the very center, I should be able to find the torque of it, right? So how do you find the torque now? The torque, okay, what is the distance here? This is A, okay, this is A and this is also A. So 2A is the distance of separation between the positive charge and the negative charge of the dipole. Now, if this is my center and if I need to find the torque, then what will we take? This vector, so that's going to be my R vector, R cross F, right? So torque due to the positive charge, torque due to the positive charge, or the F also, the torque due to that force, not positive charge, I should say. The torque due to force F plus is actually R, this one, R cross F plus. Okay, but what is it R? That R is actually A vector in that direction. I'll put it as A, right? So A cross F, R cross F. So A in the direction. I put that way. Okay. So that gives me what? It gives me what is the magnitude of this? The magnitude is going to be A, F, and then sine theta, right? That is this angle. That's the angle between these two, right? It's theta. Theta is angle between this R vector and then this F vector. F vector is like this, R vector is like this. So AF sine theta. And then what is the direction of it? Well, it's going to do it this way, right? So F this way, R cross F, R cross F. So notice that my thumb is going into the board. So the torque vector actually goes into the board. So when it goes into the board, then I can do a cross for it. That's the direction. I don't know if this has been taught to you. You think of it as an arrow. Okay? Like when you do the vector product, you think of the resultant vector as an arrow. So, and I'm looking at it here. So the arrow is going this way because R, this is F, this is R cross F. So the arrow is going into the board. If the arrow goes into the board, it's like this, right? This is the arrow, bow and arrow. If the arrow goes into the board, what would I see? I would see the back of the arrow. So the back of the arrow will have this plus sign, right? I have this. If I look at it from here, the arrow goes in, then I should be able to see this one. It goes in. But when the arrow comes towards me, then what would I see? I see the tip of the arrow. So when it comes towards me, then dot. So this is the tip that is coming towards me, and this is the width of the arrow. It's like that, right? Arrowhead. So it's like that. So it's going to look like this, and because it's going to be like this. So this is the diameter I'm going to see here, and then this is the tip I'm seeing. So you are going to use the same convention for the third vector in a cross product. So when you have A cross B, then the arrow goes into the board. When the arrow goes into the board, then I should be able to see the back of the arrow, which is this. When the arrow comes to me, for example, if I have A cross B, the arrow comes towards me. When it comes towards me, I see the front of the arrow. So these are the symbols I will use to describe it. But in this case, the torque vector is going into the ball. So that's how it is for this force. Okay. Next, what about the second one? The torque due to this. Okay, torque due to the negative force. Okay, that is again going to be equal to. Okay, this is here, like this. Correct? So it's in this direction. So A from the center, A is down, F is like this, A cross F, right? Or cross F. But this A from this center has this direction, right? It has this direction. Okay. I'll assign a unique direction for it. Okay, first of all, I'll use the unique direction is going to be the direction of the dipole moment. Okay, I'll take that as a reference, and I'll see which direction this is and this is with respect to the dipole moment direction. Fine. For the dipole moment P, let's see, for the dipole moment P, what's the direction here? First of all, dipole moment P is actually 2AQ, and in the direction of the dipole moment, it's 2AQ, unit vector along the direction. Okay, so what is that? It will go from negative to positive, right? So this is direction of P. This is the direction of P. So A in this case is in the same direction as P. But A in this case is in the direction opposite to P, because it's 0, this A, it goes like this. But P is in this direction, negative to positive. But if we take this A direction, it's down. So that is minus A, or minus A into unit vector P, right? It's better. Put it that way. Or I can, this is minus A into unit vector P. The same thing, A into unit vector P would be there, but I have not considered that in the first case. But I can do it that way also. But now I'm making it more clearer for you. So this is for, if I take this one, and minus A in this direction, and F is in which direction? F is the direction, opposite direction of, so F minus is the direction, opposite direction of F plus, right? So this can be written as minus F plus, right? Direction. Same magnitude, but in opposite direction, F plus. Yeah. And this minus and minus will become plus, then you will effectively end up with what? This is going to be equal to A cross F plus is equal to AF sin theta. And then what's the direction? Again, it goes inside, right? So this A, F minus A cross F. See, the arrow is still going into the board. The vector cross product, it's going into the board. So, is this. It's pretty obvious, it's intuitive. You don't even have to know this. Look at this. From the center, I'm going to, from the center O, my A is in this direction. Correct? That's my R cross F, right? A and cross F. F is in this direction. R cross F goes in. Again, what happens here? A in this direction. Because from the center, that's my R. A is in this direction. F is in this direction. R cross F. Again, goes inside. So, the torque due to this F plus and then the torque due to F minus, they both act in the same direction. So then what's the total torque? So the total torque tau can be given as torque due to the positive charge plus torque due to the negative charge. And in this case, both of them are in the same direction, so they just added. So I'm going to have AF sine theta plus AF sine theta, both of them in the same direction. Direction is this. It just add up. So that gives me the torque is actually equal to 2AF sine theta in that direction. Okay, so this is the direction. Okay, so let me expand on this now. So 2A, then F is QE, right? So QE sine theta to this direction. So now what is this? 2AQ, that's P. So you got PE sine theta in this direction. That's my 2. Very good. I got P, I got E now. Now can I express it in terms of P and E? Like the torque, basically the torque, you see. How do you write torque? The torque is actually R cross F, right? R cross F is how we write it. So from there only we got all this stuff. But now we got this torque, this particular torque experienced by the dipole is given by P, E and sine theta. Okay, right? So P is here, E is there. So then again P is in this direction, E is in the direction, and like E is in the direction. Instead of A cross F, now I can write as P, E. But is it E cross P or P cross E? Let's see. Let's say that it's E cross P. The sine theta would be the same, right? There is an E, there is a P. The theta would remain the same, sine theta would remain the same. But now what if it is E cross P, then what happens? E is in this direction, P is in this direction, E cross P is EP or PE sine theta. What is the direction? Notice, it's in this direction. Did you have the direction? No. So I cannot have E cross P. E cross P will give me the same magnitude, alright? But you see, I get the direction wrong. But what if it is P cross P? So P is in this direction, E is in this direction. So P cross E is PE sine theta. And notice the direction is right. So now I can write this tau as equal to P cross E in vector form. Okay. So this is a torque experienced by the dipole when it is kept in a uniform electric field. Again, as I said, we don't know the nature of the system that produces this uniform electric field. We have not talked about it, we'll talk about it later. But supposing that it is maintaining a uniform electric field in the space, then if I keep a dipole in that field, then it's going to experience a torque, and the value of the torque can be given by this expression tau is equal to P cross E. So you move from torque is equal to R cross F to P cross E for this dipole in this setting. So I hope you understand this. There are a couple of things I need to say. Well, this is a uniform electric field. Wonderful. So the force experienced by the positive charge and then the negative charge is the same in magnitude actually. In magnitude, the directions are different but it's the same magnitude. So the first point here is that the force experienced by positive and the negative charges the same, okay, the same. in magnitude. The directions are different. The directions are always opposite. So the net force is 0. So the net force is always 0. So net force is always 0. Okay? This force or this force. The net force is always 0. But the net torque is not 0. You notice here. There is a torque due to this, there is a torque due to this. Net torque is not 0. So the system is not going to be in equilibrium. For mechanical equilibrium, you need to, from your 11th standard, if you remember, then sigma F must be equal to 0, and then sigma T, the torque, the toe, must also be equal to 0. Here, the sigma F is 0, but sigma toe is not 0. It's a non-zero. Okay. So it's not in equilibrium. That's why it's not going to be stable like this. It'll start moving. It's not in mechanical equilibrium. So the force experienced by the positive and the negative charge is the same in magnitude. But the net force is always 0. Okay. But when will the torque will also be 0? When it is in this position. When it is here. See, it's a varying torque actually, because notice it's a varying torque. Why? The sine theta, the angle is changing as it moves like this. It's a varying torque, it's not a constant torque. They experience constant forces, but the torque is actually varying. Why? Because angle, as it moves down, the angle is going to be changing. The sine theta will be changing, and when it is exactly here, then the torque will be 0. At this position, torque will be 0. Again, when it comes here, the torque will not be 0. Now the torque will revert. The torque will be in the opposite direction as it comes down. The torque, think about it. So you have I'll take this case. Okay? Suppose it's like this. It's come like this. So the positive charge from here it has come down to this position. You see now the force will be in this direction, but now the A is in this direction. So it's A cross F. The torque is in this direction, notice. So the torque will act in the opposite direction, try to restore it. Okay, that's what I was trying to say. Okay. So the force experienced by the positive and negative charges is the same in magnitude, but the net force is always 0. But the net torque is 0 at this position. Because the sine theta is 0, because theta will be 0 when the forces are aligned. In the same direction. Okay. But then it will be changing again. You have varying torque here. Wow. So that is one thing. So net force is 0, but the net torque is 0 only when the dipole is parallel or anti-parallel to the field. In this case, you have varying torque. Okay, you do not have a constant torque here. You have varying torque because theta, even though P and E are the same, these magnitudes are the same. Theta is changing, so you have varying torque. Okay, so that is one point. Okay, but what happens if I'm going to keep this definitely gives you another idea. I've talked about uniform electric field. Now, what happens if I keep the dipole in a non-uniform electric field? The electric field is not uniform. For example, I have E1 here and then E2 here. Okay? So let me take this one, non-uniform electric field. So you see, I have E1 here, this point, and then E2 here. So this is going to be E2. And then I'm going to have, say, maybe E1 here. Something like this. Okay? But then this is dipole. So this is plus Q and this is say minus Q, something. Minus Q. So what happens now? You see, even if it is going to be acting in the same direction, suppose even if E is in the same direction, let's say as E1, but then the magnitude is different. The magnitude is different here. So what happens now? There will be a net force now. Right? There is QE2. Here it is minus QE1. So there will be a net force. There will be a force of attraction in this direction. But then that would be F1. There will be a force of repulsion in this direction. That's going to be F2. If this is greater and this is smaller, then there is a net force. So that net force will try to push the dipole in this direction. Suppose if F2 is greater and F1 is smaller, then what happens? There is a net force in this direction. So the dipole will try to move in this direction. At the same time, they are not aligned, they are not acting along the same line. You see, this is moving in this direction, pushing in this direction, this is pushing in this direction. You see, there is also a torque here. So what this will do is, it will move and then it will be vibrating and then it will be moving. Okay. So it will do this as it goes this way. In this case, it will just be doing this because the forces are equal and they cancel each other out. So it will be vibrating like this in uniform electric field. But in a non-uniform electric field, suppose this is greater and this is smaller, then what happens is it will do this, vibrate, and then it will do this like this. It will move in the direction depending on which field value is greater, E2 or E1. So the non-uniform electric field, net force is not zero. Net force is not zero. Yeah? Also, net torque is not zero. Maybe there is a special position where it is zero, the net torque is zero, but it doesn't matter actually. The net force is not zero, the net torque is not zero. Here, the net force is zero, but the net torque is not zero. Here, net force is also not zero, net torque is also not zero. Okay? I hope you understand this part. So this is what happens when you keep a dipole in an electric field. I hope this is clear to you. Okay, to illustrate this idea, I'm going to do a problem. But there is no problem in your textbook as an example. So I'm going to take an exercise problem and explain this idea to you in more detail. Now I'm looking at problem 110 in your exercises on page 46. I'm not taking any problem from the examples in the textbook. There is no example given for this. So I'm taking a problem from the exercises to explain this to you. And the problem number it's an exercise problem number 110. Exercise 110, not example. Let me read the problem to you. An electric dipole with dipole moment 4 × 10⁻⁹ coulomb meter is aligned at 30 degrees with the direction of a uniform electric field of magnitude 5 × 10⁴ Newton per coulomb. Calculate the magnitude of the torque acting on the dipole. So, what I said, they're talking about a uniform electric field. So, the net force is 0, right? So, uniform electric field. So, the field is like this. The E value is given. Okay? So, E, the field value is given to be 5 × 10⁴ Newton per coulomb. It's 5 multiplied by 10⁴ Newton per coulomb. So that's it. That's my E here. And then I've given you a dipole moment, which is P. Yes, I have a dipole here. Let's say I have a dipole. This is my plus Q, and this is my minus Q or something. So this is my dipole, and it has a dipole moment P. Okay. So this is P, that from negative to positive. So that dipole moment is the value of it is given to be 4 into 10 power minus 9 coulomb meter. So 4 into 10 to the power minus 9 coulomb meter. And it is aligned at an angle of 30 degrees to the field. Now it is at an angle of 30 degrees to the electric field. Now they want you to find the torque acting on the dipole. Okay, so what do we know? So we know that the torque acting on the dipole at any given moment is given by the expression tau is equal to P cross E. Right? Okay. P cross E. Small p cross E now. Okay, which is equal to P is sine theta. That's a magnitude. P E sine theta. And then you are going to get direction for it. I mean, it depends on which direction E is and which direction P is. I've chosen this to be like this, so I can assign a direction to it. But that's arbitrary anyway. Okay, so when the dipole is at an angle, the dipole which has a dipole moment P is at an angle 30 degrees to the electric field, the external electric field which is uniform, then what is the magnitude of the torque experienced by the dipole? So that's easy, right? Okay. So what is P value? P value is 4 into 10 power minus 9, and E value is 5 into 10 power 4, and then sine theta is 30. Okay. So that's a magnitude. But for this picture, which I've drawn arbitrarily, randomly, the direction of torque also can be assigned, but that is not important. But if you want to assign a direction to the torque, and I will put it like, so P cross E goes in, so this will be the direction, goes in, into the board. So that's the direction, into the board. But that's not important. Even if I've chosen E to be in this direction, then P to be in that direction, then it could be slightly different. Okay. Direction could change. They're not bothered about it, they're bothered only about the magnitude of the torque. Okay, so that's the magnitude. So what I'm going to get now? So 4 into 5 is 20. So it's 4 into 5, 4 into 5 into 10 power minus 9 into 10 power 4, and sine 30 is half. So that gives you 2, then 10 into 10 power 4, 10 power 5, then you got 10 power minus 9. So I'm going to have 10 power minus 4 Newton meters. Right? Because you have Newton per coulomb and coulomb meter, coulomb and coulomb will cancel, then you have Newton meter. That's the unit for torque anyway, R cross F. F is Newton, R is meter, so we'll get Newton meter that way. So this is what we'll get that. So that is my torque. The magnitude of my torque is this. When the dipole is aligned, when the dipole makes an angle of 30 degrees to the applied field. But notice that this value would not remain the same. Right? Suppose if it was aligned at an angle 45 degrees. Then what's going to happen? If this was aligned at an angle 45 degrees, then, okay, I'll do this. Your problem is over here. This is a problem asked in the textbook. That is done. But I'm going to use another case now. Case 1. Case 1 is when theta is equal to 45 degrees. So when it is making an angle 45 degrees to E, then this will change. What is tau? Tau is equal to 4 into 10 power minus 9 into 5 into 10 power 4, that which is, this is P and this is E. Now we see sine theta, right? Sine theta. Now sine 45 is going to be 1 by root 2. So when it is at this position, then you are going to have a different magnitude for the torque. torque. Okay, so that would result in root 2 into 10 power minus 4. Okay, with the 10 power minus 4, the root 2 is what you will get here. If you do that properly, then correct. So this is going to give you root 2. I can write this as 2 into 2, and this can be cancelled. I can get root 2, and then the rest of the things will come. Then I'm going to have root 2 into 10 power minus 4 Newton meter. See, the torque is going to change. But if the dipole was like this, making an angle 90 degrees, well, in case 2, the angle is 90 degrees, then my torque value is going to be the same 4 into 10 power minus 9 into 5 into 10 power 4, which is P, which is E. But now you see sine 90, sine theta part, it's going to be 1. Right? So that would give me 20. So 2 into 10 power minus 4 Newton meter. Same P and same E. But depending on how the dipole is oriented at any particular point in time, the torque experienced by the dipole would be different. Even though your textbook talks about only this case, you need to understand that as the dipole is moving in the electric field, it is going to experience varying torque. The magnitude is going to change even though the direction remains the same. Okay? So I want you to understand that, and that is why I thought it best to do this problem along with that explanation I gave you. Okay. Hope this is clear to you. It's a very important idea because you will be using it again in the next lesson when we calculate the potential energy and all that stuff. So I want you to understand this properly. As I said, like everything is connected to everything else in physics. So this is connected to 11th standard. Notice, so torque is R cross F. That's where we started. So everything is connected to everything else. So like what you learn here will be used in the upcoming lessons too. So understand this properly. Okay, so again, to summarize, if we keep a dipole in a uniform electric field, the net force on the dipole is 0, but the net torque on the dipole is not 0 except in one position. Okay. But if we keep the dipole in a non-uniform electric field, the net force on the dipole is also non-zero, and net torque is not 0 anyway, except maybe one position where you might get one or two positions where the angle will become, so sine 0 or sine 180. That's when, you may probably get the torque to be 0, but that's in one position. But the idea is this: in uniform electric field, net force acting on a dipole is always 0, but the net torque is not 0. In a non-uniform electric field, the net force acting on a dipole is not 0, and the net force acting on the dipole is not 0, and then the net torque acting on the dipole is also not 0. So in a non-uniform electric field, in a uniform electric field, the dipole will just oscillate like this. But in a non-uniform electric field, the dipole will oscillate and then will also move. That is the net force. Hope you understand this.